Alright, what we're looking for in this problem is to find the maximum acceleration experienced by the bungee jumper. And the first thing you have to really do is figure out where that might be. Well, it's not going to be at the top, most likely, because that's where the person is going to be accelerating due to gravity. So this is all just gravitational accelerations that take place really from 1 to point 2. Just to quickly acquaint you with what's going on here, at point 0 the person is just looking off the bridge. At point 1 the person has jumped off the bridge but is still at the same height, so they've just left, and I would identify this as having a velocity of 0. At 2 we definitely have some sort of a downward velocity, so it's greater than 0. The absolute value of it is greater than 0. And we still have, all throughout this phase, just the force of gravity acting on the person. So that's the only force that we would really have to take into consideration. So we've got force of gravity, and there's nothing else really acting on the person. Between stage 2 and 3, however, we start to get what we would call a spring force. So a force from the spring as well as the force from gravity. And the thing is that ultimately the spring force has to exceed gravity if it's going to stop the person. If the force of gravity were just equal, so if the force of gravity plus the spring force equaled 0, that would mean that the acceleration was 0, but it would mean that there was still a velocity downward since the person was already falling. But what we know to be the case is that the person stops and eventually comes back up, so the velocity at 3 once again equals 0. So that gives me a hint as to where the maximum force and the maximum acceleration will be. My guess is right around here. So once the person has gotten to the point where the spring force is maximized, we're going to have a large acceleration upwards. Just to give you another explanation for why this is so, gravity has a full 31 meters to accelerate this person at a constant rate. The spring only has, the bungee cord, only has 19 meters to completely counteract 31 meters of downward acceleration from gravity. So the fact that it has less of a distance to do the same amount of work suggests to me that the bungee cord is going to be accelerating the person more rapidly on average. Now, how do you go about actually solving this problem? So to me this looks like a conservation of energy problem. I don't have any non-conservative forces that I need to worry about, so I can go and say energy initial equals energy final. I'm primarily interested in stage 1 to stage 3. Now you might be thinking, why can't I use forces? Well, the issue here, while we're looking for the maximum acceleration, in order to find that maximum acceleration, we're going to have to make use of these two, and they'll actually be equal to an m times an a. We won't have 0 acceleration. Okay, so we're going to be looking for where we have gravitational and spring forces, and we're going to need to know k and x, if that's the case. So we need to find k. We can't just use a sum of forces at any old point, because the spring force is constantly varying. So what we need to do is make use of the idea that the net work equals the change in the kinetic energy, which is 0. We could use this approach, or we could use the conservation of energy approach. If I go through my list of questions that I can ask myself, so is it moving? At point, and actually I should say this is 2 to 3. Actually, no, this is 1 to 3. That's right. So we have from point 1 to point 3. Is it moving at point 1? No. Is it moving at point 3? No. You might be thinking, why not use point 2? The reason not to use point 2 is because there's more happening there, and there's less that I know. So it just doesn't make sense to actually make use of point 2 at the current time. If I ask, can I fall? The answer is yes here. And the answer is yes here, but we'll just make this our lowest point. So we're going to make this h equals 0. Because we're hoping the person doesn't fall past this point. Then we ask the question, is it attached to a spring that's stretched or compressed? So this part is partially affirmative. It is attached to a spring, but it's not stretched or compressed at this point, so no spring potential energy. Down here, a definitive yes, because it is attached to a spring, a bungee cord, and it is stretched. And as I said before, we had no non-conservative forces to worry about. So this is shaping up to be actually a pretty simple problem. You set your gravitational potential energy at 1 equal to the spring potential energy at 3. And we have mgh equals 1/2 kx 3 squared. And here's where we have to keep track of some things. My x3, and I think I used y here. So, well actually, y was the total distance. So my x for the spring, I have that labeled here. That's going to be -19. The actual height through which we fall is going to be 31. So h equals 31 meters. So these are the things that I definitely need to know. And so then I can just solve for the k value. So k will be equal to 2 mgh L1 compared to x at 3 squared. And if I plug in all my numbers, I get that it's about 101.1 newtons per meter is the spring constant. So that's how I figure out what the spring constant is. Now, I already kind of previewed what I'm going to do for the next part. My next part is just going to be finding out what the force is so that I can get the acceleration. So I do sum of forces equals m times a. This is what I want to find. I know that I have the spring force and the force of gravity equals m times a. And I'm looking at this. This is at point 3. So my spring force is just the opposite of k, x3 minus mg equals m times a. Bear in mind that my x3 is a negative number. So I'm just going to divide by m. And I'll have the opposite of k x3 over m minus g equals the acceleration. If I plug everything in, what I should get then is an acceleration of 22.2 meters per second squared, and it is positive. It is a positive number. The reason that it's a positive number is because we should be accelerating upwards, and that's about it. Now, one thing that I do see, and you can stop it now if everything makes sense, but maybe you got the wrong answer. Maybe you got about some factor of 2 of this. A lot of times why that occurs is if you didn't calculate the k value correctly. If you use sum of forces to get the k value, it's very possible that you would get a number for the acceleration that's off by a factor of 2. So you definitely need to be careful. When you have a varying force, make sure you use that conservation of energy to help you out. If you want to know what's going on at a particular point, independent of any other point that's ever happened, then this one will do it for you, sum of forces. But if you want to look and see what is the change in the motion of the object, or what is a comparison of the object now compared to how it was before, and you have a non-constant force, you definitely need to use energy to help you out.